Okay, guys, welcome back. We are going to be going through the ninth problem of um, Project Euler. And I'm going to go through three different ways to do it. I've got the answers already here because there's a lot to type up, and I figured it would be simple to just um, have it right here. That way I make sure I'm typing everything correctly, and I'll recreate it as we go along. So the prompt that we're given is a Pythagorean triplet is a set of three natural numbers where a is less than b and b is less than c, for which a squared plus b squared equals c squared. We know what a Pythagorean triplet is, right? It's the lengths of a different side of a triangle with, or a right triangle with whole numbers. There exists exactly one Pythagorean triplet for which a plus b plus c equals 1,000. And we are tasked with finding the product of that. So let's get started. Um, the simple way to think about this is that there is a relationship between these three numbers, and that relationship is equal to 1,000. That their sum is 1,000. So intuitively, we want to say there's three. We just iterate through each of those. We check to see if it is equal to 1,000. Then, in addition, where you would check to see if their powers, or the two of them, a and b, each squared, are equal to the third one, c squared. So, just to show you what that looks like, obviously you see it here below. We don't need to start it at 1. We can start at 3. 3, 4, 5 is the smallest Pythagorean triangle, so that's where we can start out. You can start at 1. Don't start at 0. That would be dumb. And then you want to say, I is less than the limit. Now, because it's the first one, you know some facts about a. Because a is less than b and b is less than c, you know that the a value has to be no greater than a third of the sum, because there has to be two numbers larger than it, and you can't have one third of a number plus more than one third of a number plus more than one third of a number equal to that number. So you can say divided by 3, and then you iterate by 1, right? But we still need to get the inner loop. So we would, inside of this, and we'll just comment that out, we'd say, inside of that, we'd have another one for, j, and then we would set it to I plus 1, because it's got to be greater than a, right? Is less than, again, less than the limit. In this case, instead of being less than the limit divided by 3, the b value can be greater than that. Greater than that? Yeah, it can. Yeah. So, but it can't be greater than a half. Because if that's the case, if this is half of it, this has to be greater, and then you've got one half of the number plus a number larger than half the number. You can't have that if for example, two plus a number greater than 2 can never equal 4, right? So, lastly, to find the third number, we would initialize another one. K, this would be j plus 1. And then once we have all those, 1, then once we have that, check to see, does a squared plus b squared equal c squared? If yes, does it also, is the sum of a, b, and c 1,000? And if both of those answers are yes, then you know to return the product of A, B, and C. Now, I could go through this whole thing, and it turns out that there could be no answer to it if we pass in something other than 1,000. Now, we know in this instance that 1,000 works, but we want to have, if we want to use this for other values to make sure, we want to have something to make sure that it does run. So just to show you what this looks like, let's see, 009 D. So it does work. You can see that it's very slow. These are the two functions that I have below that speed it up. We can test it out. I believe 100 doesn't work. So let's go ahead and try that out. Yeah, nothing found. I believe 60 works. Let me test that out. Yeah, it does. Yeah, okay. And I think 12 should work too, right? Let's see if 12 should work. That's the 3, 4, 5, right? So it works. It's not that fast though. Even when we went to the first one, it's still far slower than anything that these could do. We could never get this to run faster than this. Well, we could. We'd have to make this enormously large though. So let's see if we can try to make it faster. What do we know? Well, we know A plus B plus C is going to equal a number that we pass in. Once we have A and B, we actually don't need to iterate through C because C can only be correct one time for every A and B value. So what if we said up here instead, K equals the limit minus J minus I. And that's what we get right here. Now I've declared these here. It doesn't really matter in the grand scheme of things. If this were something that we're running more regularly and a lot more frequently, it would save some time to have it declared up here. It's not a huge deal. It's not going to shave off a ton of time. You can see though that we've done the same. A equals 3, B equals A plus 1, and then instead of C, a loop for C, we say C equals the limit, I've named it here num, minus A minus B. So what does that mean? Well, we know that we don't need to actually check for this now too, because we know we've just designated it to equal that. So we only need to check to see if C squared is equal to A squared plus B squared. Now you'll see I've written it here differently. There's 3 different ways you can write it. These are 2 of them. I think in the last one I bring up the other one. But when you want to square a number, there's 3 different ways to do it in JavaScript. Obviously, this is just C times C, math.pow, and I think I'll show you a different way later on. If I don't cover it in the last function, I'll just show it. But you already know from this that it works. Well, I know that this is the correct answer. And all of these are giving the same answer. So either they're all broken or they all work. So unfortunately, it looks like we cannot reduce this any further because we can't make B and C both equal to just something in terms of A. That's kind of an issue because that's exactly what we'd like to do. So what are our options? Well, as it turns out, some enterprising Greeks long time ago discovered a way to write A, B, and C in terms of 2 different variables, m and n. A squared or A equals m squared minus n squared, B equals 2 times n, and C equals m squared plus n squared. That's only 2 variables. And we know from up here when we had 2 variables, or 2 of the 3 variables, we could write the third one in terms of the other 2. hopefully that means that when we have just two variables, having one will allow us to write the other in terms of that. So if we know that a plus b plus c equals the input value that we're given, then we also know that this equals a, this equals b, and this equals c. So they should also equal the input. We can rearrange these terms and get this function right here, this equation right here. N is equal to the input divided by 2 divided by m minus m. And with that, we can eliminate the need for an additional loop. So let's take a look and see what that looks like. We're going to initialize m at 0 here. We can actually, I think, initialize it at 2, but the first step that's going to, or no, we can't. We have to initialize it at 0, I believe. Well, we can initialize it at 1, but it misses 3, 4, 5 if we tried to find 3, 4, 5. And then the first step we do is iterate it. And there's a reason why we do, but we'll get into that. We have this Boolean value is found equal. It's going to be set to false. And the biggest thing is that n gets written as a function. And this function is this right here. So anytime we call n, we evaluate the value of m at that moment. Num doesn't change. We could put in the num value, we could just, I don't know, we could have set num to a constant or whatever, but whatever. That's always going to stay the same, but m does change, which is why we need to reevaluate it. Okay, so while is found as false and m is less than the number, we're going to start off by incrementing m. If m is less than, let's evaluate n, and n is an integer value. Now this is important because this equation sometimes can yield a non-integer value for n. So we do want to make sure that n is an integer value. And n is also greater than 0. When m gets high enough, n starts going negative. When m gets close to close to the value of half the input, n is going to start going negative. So we need to make sure that we're not pulling it. If it turns out that this is negative, we should break right there. There's some different things you can do to to break for that and stuff like that. This is just simple. Just let it run. It's not too big of a deal to let it run for false values anyway. Not our primary concern. So, but if m is greater than n, and n is an integer, and n is greater than 0, then we know that we have found the m and n values that we need to return. And why is that? Because n is written in terms of the limit number that we passed in. So it's not easy to see. We didn't just find two random m and n values and you're like, yeah, that's great. Let's turn those in and call it a day. No, n is being written in terms of the limit value that we passed in as well as m. We're iterating through m. N is written in terms of that m and the limit value. The limit value is not changing as we're iterating, but the m is. So when we suddenly find something that fits all three of these, we know m and n work. So we can set it to true and exit. Now, this can also exit other than is found turning to true. So we do want to check to make sure that we haven't exited while m is not an integer or m isn't less than 0. Those are two things that can happen once m gets big enough. So we check that first. If either of those yield a yes, we'll say nothing was found. And then we can go ahead and you'll notice this is our c value, m squared plus n squared. This is the other way to write exponents that I mentioned above. You can just put this little asterisk and that's going to put it to the power of 2. n squared times the a value, m squared minus n squared, times the b value, 2 times m times n. And there you go. You can already see that it worked. We can even try different values. Instead of trying different values over here, though, I thought maybe it would be interesting to run a little bit of Jest. This is a testing framework or a testing tool that you can use within Node. You just have to install it with npm. You have to obviously install Node first. It's going to take a while to run. Yeah, good. I did block out. So these are the tests that I'm running for this problem. And I think it should take a full minute. It does take a while. It's obviously checking 12 different ones, which, takes a while on its own, but Jest in any framework also has some stuff going on its end that it needs to do, which adds to the time for each of these to run. So in the first instance, this is for the 3, 4, 5. I can't remember what this one is. I think it's 21, 20, 29 is the C value in that instance. It's 20, 21, and 29. And the product of those is this. And then this is obviously the answer that we've been working with through Project Euler. And then we've got one down here just to make sure that nothing found works. So when this is done running, and it just finished, look at that, minute long, all of these passed. All of these were found to be accurate. When we pass in a value of 50, each of the functions return a value of nothing found. So the syntax for Jest is expect. You can see up here I've required expect from Jest. To be num.solution. That's the solution. That's the value that we're passing in. So this is the value that we're testing, and we're expecting to get a return value of this. So that's about it. This is I'm closing in on as much as I've got left for Project Euler. There's on their website, they sort of ask that people only go over the first, I think, 100 of their problems. And there's kind of frequently you'll only see people talk about the first 10. So you can see I've got some other ones going on over here. One of those is not finished, still being worked on by me. But so I'll try to come up with some different material. But I thought this would be a good opportunity to talk about ways that you can think about optimizing your code, because this one is simple enough to grasp. This one takes a little bit more effort to think about. And this one is obviously superior, but it takes a little bit more brain power. Maybe a little bit of Googling around, see what the ancient Greeks found out, 4,000 years ago. So I hope that was interesting. As always, drop a like, maybe comment, hit the subscribe button, and let me know if you guys want to see anything else. Bye.